This is David Wethey. I'm going to talk about our poster on ECOSTRESS Radiance bias correction by quasi-simultaneous Nadir overpass comparisons with CrIS and IASI hyperspectral sounders. We've used hyperspectral sounders as reference instruments for doing a bias correction of the ECOSTRESS instrument on the space station. We've used G6 intercalibration system criteria, including acquisition within 30 minutes. The scenes need to be in similar orientation. The standard deviation of the ECOSTRESS brightness temperatures within each footprint of the sounder have to be less than 0.05 K. An example of a sounder footprint holds somewhere between 20,000 and 40,000 ECOSTRESS pixels. What we do in this process is we convolve the IASI spectra with the ECOSTRESS spectral response functions to calculate the radiances associated with individual channels of the instrument. The CrIS instrument only covers 2 of the ECOSTRESS channels. The IASI covers all of them, and in fact covers also Trishna, SPG, and LSTM channels. The biases are quite remarkable. The uncalibrated ECOSTRESS Collection 1 data have an overall cold bias and skin temperature retrievals of about 1.1 K, and each of the wavelength bands has a cold bias. They also have generally a positive density dependence of the bias. The graphs here are from -5 to +5K on the bias axis, and between 240 and 320K on the horizontal axis. Collection 2 was a correction done by JPL, and it increased the temperature dependence of the biases, but reduced the average bias to approximately 0 in all channels. Our correction method reduces the temperature dependence essentially to 0 and reduces the average bias to 0. A linear or quadratic correction has approximately the same effect. To validate these analyses and corrections, we looked at a set of completely independent CrIS sounder matchups. This is a totally different instrument. It's also hyperspectral, but it's on totally different platforms. This is on the same platform as the VIIRS instrument, whereas the IASI is on the METOP satellites run by the European Union. The IASI corrections, well, the initial data, ECOSTRESS Collection 1 uncorrected, had a bias relative to cold bias relative to CrIS in both the 10.49 and 12.09 micron channels. It also had a slight positive dependence of temperature dependence of the bias. Collection 2, the corrected data from JPL, has the opposite temperature dependence and has approximately reduced the bias, the average bias, to 0, but there is this strong temperature dependence. Once we've done our correction based on IASI measurements, the CrIS biases are essentially 0, and the temperature dependence is essentially 0. And the linear and quadratic corrections have approximately the same effect. We did a completely independent second validation using radiance transfer simulations at triple matchups to IQUAM in C2 data and geostationary observations flagged as cloud-free. Prior to the corrections, the bias patterns are the same as what we saw in the IASI measurements. The ECOSTRESS Collection 1 data have about a 2-degree cold bias. The ECOSTRESS Collection 2 data have approximately a 0 average cold bias, but an increased temperature dependence of that bias, especially at 12 microns. And our IASI corrections reduce that cold bias to less than 0.5 K. It's not quite as much of a reduction than we saw in the CrIS validation, but the atmospheric absorption is not fully characterized by the ERA 5 reanalysis data used in the simulation. So overall, this validation is consistent with the validation that we had from CrIS. There also are non-uniformities along the focal plane which have to be corrected. Here's a plot of the brightness temperature anomaly along the focal plane from pixels 1 to 128. And what you notice is that there is a positive anomaly in the middle of the focal plane. There's a negative anomaly in many of the pixels on this end of the focal plane, and a smaller negative anomaly on this end of the focal plane. Since mirror swaths overlap by about 30 pixels, on one mirror swath, this group of pixels overlaps the same geographic regions as this group of pixels. And the result of that is that when you do the geolocation, you end up with warm, cold, warm, cold, warm, cold pixels as this pixel gets mapped next to this pixel. And this leads to stripes and artifacts. When we look in detail at this situation, we find that there is a temperature dependence of this anomaly, and it varies by individual detector. So here, looking at detectors 97 to 128, we see that there's a negative temperature dependence on some pixels. Then there's essentially zero temperature dependence for a while. Then it becomes a positive temperature dependence for another group of pixels, and then back to zero temperature dependence, and positive temperature dependence, positive, 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 and then it goes negative in this group of pixels. So not only are the average anomalies differing from one pixel to the next, but also the temperature dependence differs. But once we know what that temperature dependence is, we can correct it. So when we do all of this, we get a dramatic reduction in stripe noise. So here's the original ECOSTRESS scene, and then we have blow-ups here, and then blow-ups even more of the image. And what you can see is there are stripes in the image that are on about a 9-kilometer spatial scale. As you look at them in closer detail, you can start to see the checkerboard pattern of the stripes. It's quite obvious in this region here. There's a lot of checkerboard here. There's very distinct checkerboard in this region. But after we've done our calibrations, the checkerboard pattern is largely gone, both in the this scale image and in this larger scale image. So the calibration works for reducing stripe noise once we take into account that anomaly along the focal plane. We can also reduce focal plane noise by the way we do the geolocation mapping. The way it's normally done is by a nearest neighbor calculation. So you pick the nearest neighbor to the target point within the nearest neighbor within 210 meters of the target point. Using the whole focal plane, you end up with stripes there. We use the median of the nearest neighbors within 200 meters, and we drop one into the focal plane. When we do that, much of the stripe noise disappears visually, and when you look at the effect of a gradient calculation, the gradient in the raw image is completely dominated by stripes. We've reduced it by our nearest neighbor mapping, and then if we use a more complicated low noise gradient operator, we can get rid of even more noise, and the sharp gradients are mapped in the place you expect based on the raw data. All of this process, we can go from 0.12 Kelvin noise in the uncalibrated image to 0.05 Kelvin noise or 0.04 Kelvin noise in the completely recalibrated image. So it's quite successful. So our overall conclusions, we reduced the BT bias from 1K to 0.1K. We reduced the overall spatial noise by 0.15%, and median nearest neighbor mapping reduces the spatial noise to 0.04K. These improve the detectability of SST gradients. Low noise gradient operators developed by Holoborodko improve this further. And we recommend that in the future, in order for harmonizing ECOSTRESS and the future Trishna, SBG, and LSTM missions, this kind of on-orbit calibration method with hyperspectral sounders is likely to be very important. Thank you very much.